Tuning the electron microscope is a key step to achieving high-resolution imaging. However, it may take up to a few hours to complete this preparatory step simply because the microscope has too many components and is thus too complicated inside. Here in the Muller Group at Cornell, we design a way to automate the process. An electron microscope is essentially a particle accelerator. This means we can characterize the beam quality in similar ways to an accelerator physics. Here we extract physical quantity, emittance, from images called raw keygrams, from which an experienced user can easily tell if the beam quality is good or bad. To automate the tuning process, we train a machine learning model to read raw keygrams. Then we can use Bayesian optimization to find the correct parameters of the microscope easily. The whole automated process would only take a few minutes to complete and might perform better than an expert. This would greatly help microscopists save time. Better tuning means higher resolution. Higher resolution means higher power. Thank you.
Hi, my name is Sam Levinson, and I am a CBB grad student in my 4th year. And I'm going to talk about our cesium iodide deposition system here at Cornell. We use this deposition system to deposit cesium iodide layers onto photocathodes with the goal of making them more resistant to oxidation. So we start by inserting a photocathode into our load lock here. We bring it into the main chamber where we can anneal the sample with a heater. And then we heat our cesium iodide source down here to 500 degrees Celsius, and we deposit multiple nanometers of cesium iodide onto a photocathode that is inside the chamber right now. If you zoom in inside the chamber, you can see a gallium nitride photocathode in there right now.
Photocathodes are extremely reactive. To prevent it from oxidation, we cover the surface with rose-thinnest saran wrap, such as single-layer graphene, hexagonal nitride, which allow electrons and photons to get through. However, those materials are extremely fragile. We developed a method which we call it upside-down method. First of all, we get an atomically flat surface covered by single-layer graphene, just like a flat baking pan covered by saran wrap. And then we grow photocathodes on top, just like baking a cookie. After removing cookie from baking pan, although the top surface is bumpy, the bottom surface can stay flat and protected by saran wrap at the same time. We already made protected magnesium and cesium-1 antimonide photocathodes using our method. And under scanning tunneling microscope, you can see the surface is protected and near atomically flat.
A day in the life of a niobium crystal under ultra-high vacuum. So I started my mornings by doing my daily affirmations, where I tell myself things such as, I may be small, but I'm still important. I am what make up powerful cavities that achieve high accelerating gradients in SRF infrastructure. So once I'm done with that, then I get my transfer arm out over in the other chamber, and this is when I start to head over to my preparation and analysis chamber to do my morning cleaning routine. So once I head over to that stage and I am all nicely snug in there, I backfill the UHV chamber with argon gas, and then I turn on the ion beam to ionize those argon atoms to create sort of a sputtering effect, which sort of exfoliates the first couple layers of my surface there. And then once I properly ground myself, then I'm ready for my electron beam annealing. So I use my filament power supply and high voltage source to get to pretty high temperatures, just to get extra clean and get all ready for my tin treatment, where I can make some alloy films and analyze in situ. So that's it. Thanks for joining.
Hi everyone, my name is Joshua Mann and I'm a graduate student at UCLA. Our group is studying the small world of nanostructured cathodes, or more specifically, the nanoblade. The nanoblade is much like the nanotip, except in that it extends in one dimension to make a ridge structure. Likewise, the incident field is enhanced near the apex of the structure, which greatly reduces the emission area compared to traditional cathodes. Additionally, the blade structure is thermomechanically more robust than the tip, which allows us to reach higher incident fields and therefore a higher brightness. My work specifically is in theoretically characterizing these cathodes. As we exist on the boundary between classical and quantum mechanics, we model the system using the time-dependent Schrödinger equation with an image potential consistent with the blade geometry. This provides us with an estimation of the yield, mean charge energy, and emittances, as well as methods of improving beam parameters. Finally, we are investigating the ability of different materials to undergo static or laser field emission, which tends to produce really neat plots like this one.